Okay, good evening, all. So yesterday we have just started a brief introduction about pattern recognition and machine learning, pattern recognition. So we are discussing this information theory. Okay, we said the information is associated with the some probabilistic measure. Okay, we call it as entropy, which measures the amount of information, and we also discuss about the cross entropy. Uh, I will write the equations once again. So entropy is defined as h of x, that is the indication. So uh, this is with respect to this random variable x, which is summation over I p of xi log 1 by p of xi or minus log of p of xi. Then we have cross entropy. So which is defined as summation, you can call it as h of x comma y, summation I p of xi log 1 by p of yi. And yeah, so there is one way of measuring the distance between the similarity between the two distributions of random variable, which is defined as um, KL divergence. So which is if you have two distributions p of x and p of y. So if you want to know the similarity between these two distributions, okay, this might be following a Gaussian, this might be following a Poisson distribution. Likewise, if you want to find the how similar both the distributions are for the given random variables, which is given by summation I p of xi log p of xi by p of y. So this is one more definition, and between the two random variables, we define another variable called the mutual information. Okay, sorry for the short inconvenience. Is it visible and audible? So mutual information between two random variables x and y is defined as uh, ixy is equal to summation joint probability of this x and y log of p of x comma y by p of x into p of y. So where here x belongs to the random variable x and the small y belongs to the random variable small y, uh, capital Y. So this is mutual information between x and y. That means how much information both together carries. Okay. So this scale divergence gives you what is the difference in the distributions. Okay. It does not give what is the common information among x and y. This is just a measure of similarity. Okay, this is just a measure of similarity between the distributions. This is the mutual information is the amount of information shared by both the random variables. Information shared by both random variables. So entropy is the information contained in a single random variable x. Okay. Cross entropy is the information which is uh, the information difference between these two random variables x and y. So there is one more thing called conditional entropy. So which is given as h of y given x or given a random variable x. What is the information present in y? So which is given as summation over x p of x and summation over y p of y given x log p of y given x. Right, so right in the bottom. So conditional entropy. So given the already you know something about the information. So h of y given x is minus summation over x summation over y p of x into p of x given y log p of x given y. So this is y given x. This is y given x. So everywhere y given x. So what is p of x into p of y given x? P of y given x according to Bayes rule. This is p of x comma y by p of x. So this p of x gets cancelled. You can also write this as p of x comma y log p of y given x. Okay, minus or if you take it minus, this will be 1 by. Okay, so this is conditional entropy. So when you see closely look the definition of conditional entropy and mutual information and actual entropy. So reduction in information is called, so you have h of x, some information about x, and when you subtract h of x given y. So you have some information about x, and you have also the information about x given y. Okay, then you can guess something common between x and y. So that information is your mutual information between x and y. Okay, if you have complete information about x and also the information about x given y, then you can deduce the information common in x and y. So you can write entropy minus conditional entropy as mutual information from the given math formula. Also here equations also you can just rearrange the terms. You can easily derive this result. Okay. So these things are mostly helpful in uh, pattern recognition, where we often estimate the probabilities of the given data belonging to a class. Okay, so this we have the true labels and the predicted labels by the model. So we need to see the true labels and predicted labels are close to each other. So their distributions should match, or their the mutual information or cross entropy between the two variables should be less. So all these measures are helpful to formulate such kind of uh, uh, you can formulate some kind of measure between the predicted ones and actual labels, and try to minimize this. Okay, maximize the mutual information or minimize the cross entropy. All these things you can do. So the next topic, yeah. So some distributions, beta distribution. So we have the data. What is probability distribution? It is in general the probability of occurrence of each and every sample of the data is called probability distribution. Okay, in general. So x can take any range. Since it is a random variable, we map from for some real values minus infinity to infinity, and this x can follow any distribution, any arbitrary distribution. We don't know. Okay, so if you know the distribution of the data, no need of this modeling or pattern recognition or machine learning or neural network. If the data underlying distribution is exactly known, okay, then need not process the uh, or you need not you can easily say, okay, this is the chance of occurrence of this event, something like that. Okay, so but often we don't know this. Okay, so we don't know whether the given waveform follows the distribution of a or not. Okay, or we don't know whether a particular face belongs to some person or not. All this, so we don't know how these face are generated, or how this uh, speech signal is generated exactly. So what we do is we try to fit a arbitrary probability distribution, the known distributions in mathematical. So all the natural signals or any uh, signals that is occurring in nature, they don't have any what we call defined mathematical equation for their probability distributions. Okay, you don't have any mathematical equation for the uh, distribution of the data that occur in nature. Okay, but few scientists have defined few mathematical equations which more or less are used alone or in combination to model any of the natural distributions. Okay, so in that case, first we'll discuss Gaussian mixture model. Sorry, Gaussian distribution. So this is very important distribution that we use in most of the applications. So we know the probability of x deriving from the Gaussian distribution is denoted as in general we denote like this mathematically x colon mu comma sigma. So the Gaussian distribution is completely characterized by its mean and standard deviation, which are the first order and second order statistics of the random variable. I think you know what is first order and second order. So this is like e of x. This is like e of x minus mu whole square. So these are the first order and second order statistics of the random variable. And Gaussian distribution, when we see the plot of any Gaussian distribution, so we have the center of the curve. The curve is symmetric and symmetric about its mean mu. So this is the mean of the distribution, and about the mean, the distribution is symmetric. That means right half is same as the left half. That means whatever the, for example, if you move some n units away from the mean and you got some xn and in towards the right direction, and in the same way towards the left direction also you have moved and you got some x1n, here you got x2n. So the probability of x1n and the probability of x2n both are same. Okay, so and this n units, if it is equal to sigma, some sigma value, which we call it as standard deviation. Okay. So that broadly defines this uh, spread of the data. Okay, how far the data is deviated from the mean. So that is why we took x minus mu. X minus mu indicates the deviation from the mean. So it can be, since the distribution is symmetric, it can be on the right side or left side. So we'll take square x minus mu square. So that indicates the deviation from the mean in general, a positive quantity. So we need to measure the deviation in the positive quantity. That's why we take square. So that gives you how much spread is there in the data. So if you have, it's a kind of bell-shaped structure. So you know bell. So this distribution, for example, if you take Gaussian distribution, which is having mean mu1, generally this what do you say, denote like this graphically. and you have another distribution Gaussian only, like this, mu 2 mu 2 sigma 2 are these parameters. So here the data distribution is more the widely distributed. Here most of the data is concentrated near mean. Okay, so sigma is low means all the data values are concentrated near the mean most of the time, most of the data points. So sigma is large means the data is distributed widely, okay, away from the mean. So which indicates, okay, in this case, okay, if the data is not spreaded, if it is closely concentrated the mean, so then it is means like then it is easy to analyze than this case, because for example, if this sigma tends to infinity, okay, then it boils down to a uniform distribution. Okay, so limit sigma tends to infinity, Gaussian distribution becomes uniform distribution, and all the events are equiprobable, and we don't have any conclusion. Okay, uniform distribution means you don't the information is high. Okay, and from the above rules we can say that if all the events are equiprobable, okay, p of x equal to 1 by n, if n events are there, then h of x will be maximum. Okay, so there is a graph which says uh, the probability of occurrence of x, if you take binary outcomes, so exactly at half, uh, this entropy versus probability reaches maximum. Okay, then if the probability of event is half, that means both are equally likely, then you have maximum entropy. Maximum entropy means maximum uncertainty, because it is a measure of information. It is inversely proportional to the information known to us. Entropy is inversely proportional to the amount of information, or directly proportional to the certain uncertainty. Okay. So if sigma is large, you are more uncertain. Okay, you cannot say which event has occurred, or okay, what is the frequency of occurrence of this event, like that. So if sigma is very small, then most probable events, we have some track of most probable events and very less probable events, like that. Okay. So even though if you don't know anything about a data point, you can simply uh, take the mean of the distribution. For example, you have some data and you don't know if if you feel that it follows the data variance is very low. Okay, so and if any unknown point is given to you, okay, x dash, p of x equal to x dash, you can simply in a rough way equate it to the mean. Okay, probability of x equal to mu. Okay, because the variance is low. Okay, so all the points are concentrated near the mean only. So if any new data point comes, unknown data point, okay, it is almost close to the probability of mean only. You can approximate, just approximate like that. Okay. So that is about the Gaussian distribution. Gaussian distribution actually described by the first order and the second order statistics. Okay, we will write the equation p of x equal to 1 by 2 pi square root of 2 pi sigma e power minus half into x minus mu by sigma whole square. Okay. So take any data point x, subtract the mean and divide by the standard deviation of the particular Gaussian distribution that is followed by x, and evaluate this expression for different values of x. Okay, if you know mu and sigma, then you can find p of x for any given data point. Okay, so this is inference. Okay, if you know the distribution of the data, you can calculate the probability of any given data point. Okay, but the modeling means reverse of the inference. If you have the data, you need to find the distribution. It is in general called generative modeling, but anyway, just note these two differences: inference and modeling. What is the difference between inference and modeling? So in inference, if you have the distribution, if you know the distribution, then you can find the probability of given point. Okay, or you can uh, also generate the new data points. Okay, in the modeling, if you have the data points, then you need to find the distribution. Okay, reverse. So anyway, that we will discuss later. So this is the probability distribution of a Gaussian. This is in fact probability density function. Okay, so because by graph only you should know this is a probability density function. This cannot be a distribution function because distribution function is monotonic and always increasing. Okay, so that means if you integrate this probability density function, you will get distribution function. For Gaussian, it looks like a sigmoid function, sigmoid curve, S curve. Okay, with at the mean you have exactly half, and as x tends to infinity, it tends to 1, and x tends to minus infinity, it tends to 0. Okay, this is the probability distribution function of Gaussian, which you can achieve by integrating this function, density function, from minus infinity to x. What is f(x) of x? CDF, cumulative distribution function we generally call. CDF is minus infinity to x fx of zeta d zeta. So until x you integrate the density function, you will get the cumulative distribution, which is in general probability of x less than or equal to x. Fx of x is probability of x less than or equal to x. So this is about the Gaussian distribution. So you have any doubts in this, or if you want to know anything more, you can ask in the chat box. So then we have, so these are all called exponential families. All the distributions we are discussing here, they belong to exponential family of distributions. That means we have exponential term in the density function. The next one is beta distribution. So I didn't encounter this yet, but I just give you the expression. So beta distribution fx of x or p of x is given as x power alpha minus 1 into 1 minus x power beta minus 1. Here alpha and beta are the parameters divided by beta of b of, this is a function of alpha and beta. So where b of alpha gamma beta is gamma of alpha plus gamma of beta, the gamma a into gamma alpha into gamma beta. So this is like harmonic mean of gamma of alpha and beta. So when you see the plot p of x versus x, like Gaussian distribution, if you see the plot, so this is having different curves depending on alpha and beta. So this is like alpha equal to 2, beta equal to 5, something like this. So depending on this, so Dirichlet distribution, this is also having same uh, similar kind of probability distribution like p of x. This is 1 by b of alpha into product of I is equal to 1 to k xi power alpha I minus 1. Where here b of alpha equal to product of I is equal to 1 to k gamma of alpha I. Here gamma means gamma function, gamma of summation over I alpha I. I'm just giving you the equations, but really, I don't think if you want to go into deep into these distributions, you can go. But I don't think we use these two distributions anywhere in our course. Okay, then we discuss about maximum likelihood. So this is basic. We see just So in this first unit, we are all just seeing the overviews. Okay, we are not discussing anything in full length. So we'll discuss this maximum and map, maximum likelihood ML and maximum opportunity map, ML estimation and map estimation in the next unit. So yeah, maximum likelihood. Before that, you need to know what is Bayesian rule. Okay. So which is a probability of conditional. It gives the conditional probabilities. The relation between the conditional probabilities. So you have probability of A given B and probability of B given A. So A and B are some events. So probability of A given B can be written as probability of A comma B by probability of B, and also probability of B given A can be written as probability of A comma B by probability of A. So that means probability of A comma B is probability of A given B into probability of B, and from here probability of A comma B is probability of B given A into probability of A. So when you equate these two equations, it gives both disjoint probabilities. Probability of A given B into probability of B equal to probability of B given A into probability of A, or probability of A given B equal to probability of B given A into probability of A by probability of B. So this is called Bayes rule. Here, what is the probability of A given B means, like for example, B is some observation you are making when you perform an experiment, and you want to know to which class it belongs to, class information. Okay, probability of class given observation. This is what we need in classification problem. So you have some observations like face images or voice sequences or any fingerprint images, and you need to know to which person that face or voice or fingerprint belongs to. That is the class. So that is given by the probability of generating the data given the person. Okay, assume that you have already have the person's model, okay, with you, person's distribution with you. So then the probability of generating B from distribution of A. Okay, probability of generating the observation or data point B from the distribution of A. And what is this called? Probability of observation B belonging to a class A. Okay, given B. Okay, given B, we need to find that what is the probability of this B belonging to this class A. So on the LHS, this A given B is given defined like this. On the RHS, P of B given A is defined as the probability of generating B over A from the distribution A. And P of A is the probability of class probability, and P of B is the observation probability. These are not conditionals. Okay. So now some terms we use for this in our general pattern recognition or machine learning terminology. So this probability of B belonging to a class given B is called posterior probability. And this probability of A, the probability of class is called prior probability, and the probability of B is called partition probability or total probability. And this probability of generating data from a distribution is what we call likelihood probability. So these terms are very very important. That means you need to understand this. Okay, with this example, then whatever the experiments you perform and whatever things you know, you and the probabilistic analysis of the data. Okay, what you need to know, what you need to get, what you need to compute is this. So if you have all these things, then then you can understand any classification problem, probabilistic methods. So what is posterior probability? It is the probability of a particular observation belonging to a class, given the observation has already there with you. And what is the likelihood? Likelihood, given the distribution is already there with you, what is the probability of this data generating from the distribution? And probability of A is the probability of class. That means with what probability you can, what are the chances of choosing that class. And you have known the ball and bowl experiment. There will be two or three balls, okay, and you have red, green, blue balls. So this, in a way, it can correlate to correlated to this experiment. If you have drawn a green ball, what is the probability that it belongs to box 1? This is called posterior. So green ball is already drawn, but what is the probability? It can be from B1 or B2. You need to know what is the probability of B1. So then how do you compute this one? From this Bayes rule, first you need to know what is the probability of getting a big green ball from box 1. Okay. So box 1 generates green ball with some probability because for example box 1 has some 3 red balls, 4 green balls and 2 blue balls. Overall there are 9 balls. Out of that, green ball all are identical, let us assume. Green ball have 4. 4 by 9 is the probability of getting green ball from box 1. Okay? And probability of choosing box 1. So this box 1 and box 2 may follow uniform distribution, equiprobable, or sometimes box 1 is bigger, you are more forced to choose box 1 than box 2. It may have 1 by 3 and 2 by 3 probabilities like that. So I'm divided by probability of green ball. So probability of green ball is that the overall probability you can take what is the probability of taking green ball irrespective of the boxes. Okay. So this you can ignore denominator irrespective of the boxes. You can always, there is no condition on boxing. So you can put a proportionality term here. So this is called posterior and this is called likelihood and this is called the prior. So posterior is proportional to the product of likelihood and prior. Okay, so that is the Bayes theorem. And now, since now you know the definition of likelihood, what is likelihood? The probability of generating an observation from a given distribution, which is probability of O given some distribution C. This C follows, that means P of C versus C may follow a Gaussian distribution or any other exponential or any other continuous distributions or discrete distributions. So O may lie somewhere here, and what is the probability of generating O from this distribution is this probability, P of O given C. So like let us say C1. So now we have probability of O given C2. For examples, this is C1 variable. So I'm just taking an example. The range of C1 is minus infinity to infinity. Okay. So let us say O equal to minus 2.5. Okay, this is let us say 0 and this is minus 2.5. So probability of generating minus 2.5, probability of getting minus 2.5 from this distribution is something like 0.01. So now you have the distribution like this. Here 0 is there and here minus 2.5 is there. This is C2, random variable C2. This is P of C2. So now if you take O as minus 2.5, and this probability is larger than this from the figure, if you understand. So this is like 0.23, something like that. So this is 0.01 and this is 0.23. The likelihood of O given class 1 is 0.01. So the likelihood of O given class 2 is 0.23. So the maximum of these two likelihoods is this one. So then what we can do is we can vote for this case where O is more likely to generate from this class distribution than this class distribution. So then we say O belongs to C2. This is just a simple example. So if you know the likelihoods, for example, you have n number of classes and one given observation. If you know the likelihood of this observation from each and every class, say P of O given C1, P of O given C2, and so on, P of O given Cn, then the maximum of all these likelihoods. This is likelihood with respect to C1. This is likelihood with respect to the C2 distribution. This is the likelihood with respect to the Cn distribution. Out of these n distributions likelihoods, whichever gives maximum, then we say that that O belongs to that distribution. Okay, more the O is generated from the distribution with more probability. So we'll take maximum likelihood. So this is the concept of selecting a distribution for the given observation by computing the likelihoods and taking maximum out of all the likelihoods. This is called maximum likelihood. Okay, problem setting. Okay, then okay. So in modeling, what is modeling definition? Just we discussed. From the data, you need to fit a distribution. Okay, generating the distribution or finding the distribution from the data. Okay. For example, if it is a Gaussian distribution, okay, so what you need to find is only mu and sigma. Okay, this is called finding mu and sigma. So this mu and sigma, these are called, they are statistics of the data, mean and variance of the general statistics of the data. And sufficient statistics means they are enough to generalize the distribution. Sufficient statistics. What is sufficient statistics? The sufficient statistics are the parameters. This we are also called, they are also called parameters of the distribution. So Finding all the required parameters are the sufficient statistics. Okay. So from the data you can find mean and variance. From the data you can also find the higher order terms other than e of x, e of x square, x minus mu whole square. You can also find e of x minus mu whole cube, which is called uh, skewness, and you can also find fourth order statistics x minus mu whole power 4 e of, which you can call it as kurtosis. Okay, all these skewness, kurtosis, and all other higher order statistics are not required for Gaussian distribution. If you are fitting this data to the Gaussian distribution, these higher order statistics are not required. Only first order, second order are enough. So that's why these first order and second orders and statistics are called sufficient statistics for Gaussian distribution. Okay. So for the example, you can have x is equal to 1 7 minus 3 2 4 0. So for this you can find e of x, e of x square, assuming that they belong to what we call the Gaussian distribution. You can find e of x, and so there are two kinds of statistics. Okay, or in general averages, sample averages and ensemble averages. In sample averages, whatever the data we have, we assume that is sufficient, and we will find the data average values from the data. Whereas in ensemble averages, you need to know the distributions. Okay, in sample averages, the mean is defined as 1 by n summation I is equal to 1 to n xi. Okay, whereas in ensemble averages, the mean is e of x is defined as summation over x into fx of x or f of x. Or if it is a continuous distribution, it will be integral, or otherwise it is summation over xi p of x equal to xi is the for discrete random variable expectation. So for this you need to know the density function, probability density function of that random variable. Then you can get the ensemble average. See, this is true distribution. These are the true averages, whereas these are the averages generated from the data. So so in modeling, you have the data, and the data follows some distribution p of x. You need to find this p of x from the data, and if this p of x have some parameters or sufficient statistics, okay, these are called this is called parametric modeling. So the entire distribution is defined by these parameters, limited number of parameters like mean and variance, for example in Gaussian distribution. Okay, that is parametric modeling. So there are some methods which do modeling without any parameters, that is called non-parametric modeling. Okay. This like we'll discuss that non-parametric modeling techniques in the next class. Okay, and yeah. So you go through all these fundamentals, okay, starting from the definition of pattern recognition, what is pattern, okay, and then fundamentals of curve fitting. I will share the content for curve fitting and information theory and the distributions, various distributions. Okay, go through that. Okay, until this, I think we can have mid one syllabus, the first unit. Okay, I will share the PDFs or material, reading material for this topics. So primarily we have numerical examples on this. Okay, though I didn't discuss any. Tomorrow, time permits, we can discuss. So numerical examples on data distributions, particularly Gaussian distribution, information theory concepts, and what else is there? Curve. Okay, these three concepts, I will share the reading content. You go through it today. Tomorrow we'll solve one or two example problems, and mid one will be on this. Okay. We will stop at this point. If you have any doubts, you can message me later. Okay. Thank you.